Today we're looking at heat exchangers.
Okay.
But, and get this, we're going to be using a very unique source for this deep dive.
Oh.
We're using a podcast script
Interesting.
that's meant to help people prepare for job interviews about refinery heat exchangers.
Okay.
So it's like
Yeah.
we're getting a sneak peek behind the curtain at like what the experts are really looking for when they're hiring for these types of positions.
What's interesting about this approach is that instead of just getting textbook definitions, we're going to see what knowledge is considered crucial in a high-stakes environment.
Exactly.
A job interview.
So let's start with the basics.
Okay.
What exactly a heat exchanger?
Well, at its core, it's a device that allows heat to transfer between two fluids without them actually mixing.
That makes sense.
Yeah.
But why are heat exchangers so essential in refineries?
Well, refineries are all about efficiency. Heat exchangers play a critical role in saving energy and reducing costs.
Got it.
By recovering heat that would otherwise be wasted and using it to heat other processes.
So it's like they're recycling heat energy.
Exactly.
That's pretty cool. Now, I noticed the source mentions several different types of heat exchangers.
Yes. It highlights 4 main types.
Okay.
Shell and tube, plate, air-cooled, and double pipe.
Got it.
Each has its own unique characteristics and applications.
To be honest with you, all those names kind of blur together for me.
Okay.
What's like a memorable detail about each one?
Well, shell and tube exchangers are like the heavy-duty workhorses of the refinery.
Okay.
They can handle high pressures and temperatures, which makes them reliable in demanding environments.
Got it.
Plate heat exchangers, on the other hand, are much more compact and great for situations where space is limited.
Oh, okay.
Think of them as the space-saving champions.
All right, so shell and tube for heavy duty.
Yeah.
And plate for tight spaces.
Yep.
What about air-cooled exchangers?
Those are the ones you'll see in places where water is scarce.
Okay.
Like deserts.
Oh, interesting.
They use air to cool down hot fluids instead of relying on water.
Makes sense.
Which is a valuable resource in those environments.
Right. And finally, there are double pipe exchangers.
Yes, those are the simplest type, often used for smaller scale applications.
Got it.
You could think of them as the entry-level model of heat exchangers.
Got it.
Yeah.
Now, the source also talks about this thing called fouling, which sounds pretty unpleasant.
It definitely can be.
Yeah.
Fouling is the buildup of material on the heat transfer surfaces, which acts like insulation and reduces the exchanger's efficiency.
So it's like when a filter gets clogged and doesn't work as well?
Exactly.
How do engineers deal with fouling?
Well, there are a few strategies.
Okay.
Regular cleaning is important. Kind of like brushing your teeth for heat exchangers.
Okay.
There are also coatings and additives that can help prevent fouling.
Got it.
Acting like a protective shield on the surfaces.
It sounds like there's a whole science to keeping these things clean.
There is.
Now, the source also mentions something called LMTD.
Okay.
What's the deal with that?
LMTD stands for log mean temperature difference.
Okay.
And it's a crucial factor in determining how efficiently heat can be transferred.
Okay, but in plain English, what does that actually mean?
Imagine you're trying to cool down a cup of hot coffee by pouring it into a cold glass.
Yeah.
The bigger the temperature difference between the coffee and the glass, the faster the coffee will cool down, right?
Yeah, that makes sense.
Well, LMTD is similar.
Okay.
The larger the temperature difference between the hot and cold fluids in a heat exchanger, the easier and faster it is to transfer heat.
Got it.
Engineers use this concept to optimize exchanger design for maximum efficiency.
So it's all about maximizing that temperature difference for the best performance.
Exactly.
I'm starting to see how these things are more complex than they seem.
They are.
Speaking of how things flow, I noticed the source also mentions counterflow.
Right.
And parallel flow.
Those terms describe the direction the fluids move within the heat exchanger.
Okay.
In counterflow, the hot and cold fluids move in opposite directions, which actually maximizes the temperature difference throughout the exchanger.
So it's like two cars passing each other on a highway, each going in the opposite direction.
Exactly.
Okay.
Yeah, in parallel flow, the fluids move in the same direction.
Okay.
Kind of like two cars driving side by side.
Right.
This results in a less efficient heat transfer.
Okay.
Because the temperature difference decreases as the fluids travel together.
Ah, so it's like one car is trying to cool down the other while they're both driving towards a sunny destination.
Right.
Not as effective.
Exactly. Counterflow is generally preferred because it maintains a consistent temperature difference for better heat transfer.
Okay, that makes sense.
Yeah.
It seems like every little detail matters when it comes to designing these things.
It does.
The source also talks about U-tube.
Right.
Heat exchangers.
Yeah.
What's so special about that shape?
The U-shape is a clever way to accommodate thermal expansion.
Oh, okay.
You see, when materials heat up, they tend to expand.
Right.
Which can be problematic in a confined space like a heat exchanger.
It's like trying to squeeze into jeans you've outgrown, not very comfortable.
Precisely.
Okay.
But with a U-shaped tube,
Yeah.
it can expand and contract freely.
Right.
Without putting stress on the rest of the exchanger.
Got it.
It's a simple but elegant solution to a common problem.
Pretty ingenious.
Mm-hmm.
Now tell me about baffles.
Okay.
They sound like something you'd find in a maze.
Well, they kind of are.
Okay.
Baffles are these strategically placed plates
Yeah.
or obstacles inside shell and tube exchangers.
Okay. They disrupt the smooth flow of the fluid, creating turbulence.
Wait, isn't turbulence a bad thing?
Not in this case.
Okay.
Think of it like stirring your coffee.
Okay.
The swirling motion created by the baffles increases the contact between the hot and cold fluids.
Right.
Which actually improves heat transfer.
So it's like giving the fluids a good mix to make sure they're really exchanging that heat.
Exactly.
Fascinating.
Yeah.
Now, this source also mentions something called pinch analysis.
Okay.
What is that all about?
Pinch analysis is a technique used to optimize heat recovery
Okay.
in an entire system, not just individual exchangers.
Got it.
Imagine you're looking at a map of all the heat flows in a refinery.
Yeah.
Trying to find the most efficient way to use every bit of available heat energy.
So it's like finding the weak link in a chain
Yeah.
and figuring out how to strengthen it.
Exactly.
Got it.
Pinch analysis helps engineers identify areas where they can improve heat integration.
Right.
And minimize energy waste.
Mm-hmm. Which is essential for efficiency and sustainability.
This is all so much more intricate than I ever imagined.
It is a very complex field.
The source also briefly mentions the materials used to build heat exchangers.
Choosing the right material is crucial.
Okay.
You need to consider the temperatures and pressures involved,
Right.
as well as the chemical properties of the fluids.
It sounds like it's kind of like choosing the right building materials for a house.
Yeah.
You wouldn't build a house on the beach out of paper, right?
Exactly.
Okay.
Common materials for heat exchangers include carbon steel, stainless steel,
Okay.
and even titanium for extremely demanding applications.
Wow.
Each material has its own strengths and weaknesses,
Right.
and engineers need to carefully select the best option based on the specific operating conditions.
This is incredible.
Mm-hmm.
We've covered so much ground already.
We have.
But there's still more to explore.
Indeed, we've just scratched the surface of this fascinating world of heat exchangers.
All right, so we've talked about different types of exchangers, how they fight off fouling, and some of the key concepts that drive their efficiency.
Yeah.
But this source, we're looking at this job interview prep script.
Yeah.
It goes even deeper.
Yeah.
It's like they're trying to throw the toughest questions imaginable
Right.
at these potential engineers.
And that's what makes it so valuable for us.
Right.
By understanding the nuances that come up in these interviews, we get a much richer picture of how heat exchangers operate in the real world.
For example, the source mentions a design choice between fixed tube sheets and floating heads.
Right.
What's the difference, and why would it matter in a refinery setting?
It comes down to how well the exchanger can handle thermal expansion.
Okay.
That tendency of materials to grow when they heat up.
Right.
In a fixed tube sheet design.
Yeah.
The tubes are rigidly attached to the shell.
Okay.
It's simple and robust.
Yeah.
But if there's a big temperature swing,
Right.
those tubes can't expand freely.
So it's like wearing shoes that are a size too small.
Precisely.
Not good if you have to do a lot of walking.
Now, a floating head exchanger allows the tube bundle to move independently.
Well,
kind of like having shoes that expand with your feet.
right.
It's more complex, but it can handle those temperature changes
Got it.
without putting undue stress on the system.
So it's a trade-off.
Right.
Simplicity versus flexibility, each with its own advantages depending on the situation.
Exactly. And that's a recurring theme we see in heat exchanger design.
Yeah.
Finding the optimal balance between competing factors.
Now, there's another term that popped up in the source that I'm curious about.
Okay.
Duty.
Uh-huh.
What does that refer to in the context of a heat exchanger?
The duty is essentially the workload of the exchanger.
Right.
the amount of heat energy it needs to transfer per unit of time.
So a high-duty exchanger is like the workhorse,
That's a great analogy.
capable of moving a lot of heat energy quickly.
And to calculate duty, engineers use a formula
Okay.
that takes into account factors like the flow rate of the fluids
Right.
and the temperature difference. The bigger those numbers,
Right.
the higher the duty.
It's amazing how much math goes into these things. It's not just about pipes and metal. There's a whole science behind it. Speaking of which, the source also talks about something called the Reynolds number.
You're right.
What's that all about?
The Reynolds number is a way to describe how a fluid is flowing.
Oh, eh?
Is it smooth and orderly, what we call laminar flow?
Right.
Or is it chaotic and turbulent?
And how does that apply to heat exchangers? Wouldn't you want everything to flow smoothly?
Interestingly, no.
Oh,
In heat exchangers, we actually want some turbulence.
really?
Think about stirring your soup. You do it to mix things up
Okay.
and ensure even heating.
Ah, so the turbulence helps the hot and cold fluids interact more effectively.
Exactly.
Got it.
The Reynolds number helps engineers predict how turbulent the flow will be, allowing them to optimize the design for better heat transfer.
It's like there's a whole secret language of numbers that governs how these things work. Now let's shift gears a bit and talk about those sleek and compact plate heat exchangers.
Okay.
Those were the ones that were good for saving space.
Right, exactly. Instead of using tubes, they have these thin corrugated plates stacked together.
Right.
The hot and cold fluids flow through the spaces between the plates, and the large surface area allows for very efficient heat transfer.
So it's like a really efficient radiator,
That's a good way to think about it.
but in a much smaller package.
Plate exchangers are commonly found in places where space is at a premium,
Okay.
like food processing plants or HVAC systems in buildings.
Now I noticed the source mentions gaskets
Yeah,
in relation to plate exchangers.
right.
What's their role?
Gaskets are essential for preventing leaks.
Okay.
They act like seals between the plates,
Right.
ensuring that the fluids stay in their designated channels.
Got it.
You can think of them like the rubber seals on a jar that keep everything airtight.
It's amazing how such small components can be so critical with the overall performance.
Absolutely every detail matters when you're trying to achieve optimal efficiency and reliability.
Now, there's something that's been bugging me a little. What's the difference between a condenser and a heat exchanger? Aren't they kind of the same thing?
It's a common point of confusion.
Yeah.
A condenser is actually a specific type of heat exchanger.
Okay.
Its job is to cool down a vapor and turn it back into a liquid.
Right.
Think about the coils on the back of your refrigerator.
Uh-huh.
That's the condenser at work cooling down the refrigerant.
So all condensers are heat exchangers,
Correct.
but not all heat exchangers are condensers.
Precisely. It's a subset within a larger category.
Okay. That clears things up. Now, there's one more type of exchanger mentioned in the source that sounds particularly intriguing.
Okay.
Regenerative heat exchangers.
Yes. Those are the ultimate energy recyclers.
Okay.
They have a clever trick up their sleeve.
What's that?
They use the same flow path for both the hot and cold fluids,
Interesting.
but at different times.
So it's like a single lane road where traffic goes in one direction
That's a good visualization.
and the other.
The key is that there's a thermal mass built into the exchanger,
Okay.
which can absorb heat from the hot fluid
Oh, right.
and then release it to the cold fluid later on.
So it's like a thermal battery
It is.
storing heat energy for later use.
Regenerative exchangers are often used in applications where you want to capture and reuse as much heat as possible,
Makes sense?
such as power plants or chemical processing plants.
Okay, so we've covered a lot of ground here, from basic definitions to some really advanced concepts. But I noticed the source also emphasizes
Yeah.
safety considerations,
Of course, in an environment like a refinery, safety is paramount.
right?
Heat exchangers operate under high pressures and temperatures, and any malfunction could have serious consequences.
So what are some of the key safety points highlighted in the source?
Well, first and foremost, it emphasizes the importance of understanding the limitations of each exchanger. You need to know its pressure and temperature ratings and never exceed them.
Right, it's like not overloading a truck beyond its capacity.
Exactly.
They're just asking for trouble.
The source also stresses the importance of material compatibility.
Okay.
You need to ensure that the materials used in the exchanger can withstand the corrosive properties of the fluids they're handling.
So it's like choosing the right armor for a knight.
Definitely not.
You wouldn't send someone into battle with a suit of armor made of paper, would you?
And finally, the source highlights the importance of regular inspection and maintenance.
Right.
Just like a car needs regular tune-ups to run smoothly, Heat exchangers need to be checked for signs of wear and tear corrosion or leaks.
It sounds like there's a lot of responsibility that comes with operating these things safely.
There is, but with proper design, material selection, and maintenance, heat exchangers can operate reliably and safely for many years.
Well, this deep dive has certainly been an eye-opener. I had no idea there was so much depth to these seemingly simple devices.
They truly are unsung heroes of industry, playing a vital role in countless processes.
Wow, we've really gone deep on heat exchangers, haven't we?
Yeah, it's pretty amazing.
Who knew there was so much to learn about these things?
Right.
And I have to say, going through this job interview prep material
Yeah,
has been a really insightful way to learn.
I agree.
It's like we've gotten a crash course in what really matters
Yeah.
when it comes to
Yeah,
designing, operating, and maintaining these unsung heroes of industry.
exactly. It's one thing to know the basic definitions,
Oh, go on.
but seeing how those concepts are applied
Yeah,
and tested in a real-world setting really takes the learning to another level.
absolutely. So as we wrap up this deep dive,
Okay.
what are some of the key takeaways that stand out to you?
Well, first and foremost, I'm struck by the sheer diversity of heat exchanger designs.
Yeah.
We've got shell and tube plate, air-cooled,
Right.
double pipe regenerative, each with its own strengths and weaknesses.
Yeah.
Tailored for specific applications, it highlights the fact that there's no one-size-fits-all solution in engineering.
That's a great point. It's like having a toolbox full of different tools.
Right.
You need the right tool for the job.
Precisely.
Yeah.
And then there's the constant challenge of fouling,
Yeah.
which seems to be the nemesis of every heat exchanger.
Right.
It underscores the importance of not just design,
Uh-huh.
but also ongoing maintenance
Right.
and a deep understanding of the fluids and materials involved.
It's like a constant battle against entropy, trying to keep things clean and efficient.
Exactly. And of course, we can't forget those clever design features like baffles and U-tubes,
Right.
which show how engineers are constantly finding ways to optimize these systems for maximum performance.
It's like they're playing a game of thermal chess, trying to outmaneuver the laws of physics to achieve the best possible heat transfer.
And speaking of optimizing, the concept of pinch analysis
Yeah.
really blew my mind.
Yeah. It's amazing.
It's amazing how engineers can analyze entire systems and find ways to minimize energy waste and maximize heat recovery.
It's like they're squeezing every last drop of efficiency out of these processes.
Exactly. And finally, I think it's important to reiterate the emphasis on safety that we saw throughout the source material.
Yeah.
These are powerful devices operating under demanding conditions.
Right.
And respecting those limitations is crucial for avoiding accidents and ensuring long-term reliability.
It's a good reminder that engineering is not just about innovation and efficiency, but also about responsibility and protecting people and the environment.
Well said. So for our listener out there,
Yeah.
what's the final thought we can leave them with? What's that one idea that might spark their curiosity
Okay.
and encourage them to keep exploring this topic further?
How about this? We've been focusing on heat exchangers in the context of industrial settings like refineries.
Okay.
But these devices are all around us.
That's a great point. They're in our cars,
Right.
our homes, our appliances,
That's
anywhere there's a need to transfer heat efficiently.
So as you go about your day, I challenge you to keep an eye out for heat exchangers in action. Think about the principles we've discussed,
Yeah.
the different types, the challenges they face,
Right.
and the ingenious ways engineers have designed them to work.
It's like a treasure hunt for these hidden heroes of our technological world.
And on that note, we'll wrap up this deep dive into the fascinating world of heat exchangers.
Until next time, keep learning, keep exploring, and keep asking those insightful questions.